Hello, my name is Craig Upson from Silicon Graphics, and I'm here to talk today about visual programming in data flow environments. Visual programming is not a new technique. It's been around for quite a while, nor is data flow a new technique. But the application of the two of them, the combination of the two of them together is something that is in the last 4 or 5 years become quite prevalent in computer usage, defining new paradigms in computer programming environments and, in addition, new paradigms in computer usage environments. So the contents of this talk are a brief background to visual programming, a background on data flow with more specific details about certain implementations, and examples that illustrate the application of these techniques. So this is not an exhaustive survey of the field, but more of an introduction. A survey would take, of course, several lectures. So what is visual programming? Visual programming is really it's one of two major techniques. One is the application of visual languages to traditional computer programming, meaning that instead of, as an alternative to using a traditional computer language like C or C++ or Fortran, using a visual language in the programming step. The other application of visual programming is the application of visual languages to traditional computer usage. How do users use computers without programming? And that is through a new paradigm, through this different paradigm, which is visual programming. Well, why is visual programming of interest, or why is it becoming more popular as the years go by? The reasons primarily are that the computing environment in which we live is really becoming much more complicated. Computers are getting much more complicated. The environments in which we compute are much more complicated. We're now very much used to having several computers that we are all networked together, and so running processes on a variety of different machines is very commonplace. This makes the environment much more complicated, especially in a heterogeneous environment where one machine is substantially different than another. In addition to that, there is now a large application backlog, meaning that the number of computer users have greatly outstripped the ability of computer programmers and application developers to provide applications that meet their needs. So this gives these three reasons really give rise to this last point, which is this need for reusable components of applications, the ability to rapidly build an application by plugging together little smaller pieces that the final result of which is a usable application. This is more a kind of a plug and play technique of combining some function which is a piece of a program, plugging it into another component which is another piece of a program, and together this collection of pieces form an application. And by doing so, we essentially deal with the application backlog by empowering end users to build customized applications for their needs without having to program. So let's talk about the basic types of visual programming systems. They fall into primarily three categories. The first is diagrammatic systems. These sort of evolved from old flowcharts from the 50s and 60s and 70s even, and they represent systems that a language that is, or an application that's built with this diagrammatic language, where you might have blocks that you plug together that are if-then-else statements, etc. There are also iconic systems. The second type is iconic systems, and now these are not necessarily they aren't necessarily flowchart based, but they're more building blocks that have iconic representations. And the third one is form-based systems. They are outcomes of the big emphasis toward form-based interfaces from the 1970s and early 80s, for that matter. And the uses of each of these three systems are primarily in two different ways. One is as a substitute for a traditional language, And as I said before, the second is to create new applications. So one is a lower level kind of language substitute, and the other one is a much higher level application substitute. So let's look now at each of those three systems: diagrammatic systems, iconic systems, and form-based systems. In this example, we see a diagrammatic system, basically the Nassi-Shneiderman representation of, in this case it happens to be how do you represent diagrammatically in factorial. So this is basically a computing strategy for how to represent in factorial. You see on the top of the diagram, this top wedge is basically an if statement. Is the number n, where n is replaced with a number obviously, greater than 1? If not, you take the left branch, which is the false branch, and the factorial is equal to 1, and you return that value for the factorial calculation. If indeed it is greater than 1, then you take the right branch of this diagram, and you start off, you initialize the factorial variable in fact equal to 2, and go from, and then a do loop from 3 to n, accumulating n as you go, accumulating I as you go, and then you return in factorial. So it is instead of a text-based language, I mean it's actually a combination of a text-based and diagram-based language, and this is just one glyph of this language in a diagrammatic system. If we look at the next type of system, these are iconic systems. This is an example from Iris Explorer, which is the demonstration application that we're going to be using throughout the talk. In this diagram, you can see a series of boxes that are connected together with wires. Each of these boxes represents some computational function. A box or a module executes and sends its data downstream to other modules that are connected in a left to right representation. So if we look at this image, you'll see on the far right a box that has, which you probably can't read on your screen, the word render, which is the renderer in this system. It contains an image which is the product of this data flow environment. So here the level of the language is much higher. It's now not individual assignment statements or operators, but more functions or perhaps even applications that are embedded into each one of these boxes. So each box now has ports. That means places to connect data into and connect data out of, in addition to controls. And we'll talk about that later. The third system is a form-based system. And probably the best example of that is our spreadsheets, which are probably the widest used application on all computers. And again, it's a two-dimensional language. In this case, it's a two-dimensional array of cells, and one performs arithmetic on cells, performs calculations on cells. And this is a simple example of a spreadsheet. As I said before, there are two basic uses of visual programming. One is as a programming language itself, and the other one is as a vehicle for building applications. So let's look at the first one, which is as a programming language. And here the goal is really to simplify the act of programming. Again, as computers get more and more complex, as large multiprocessors become more and more prevalent, the task of programming becomes more and more difficult. And in fact excludes more and more people from programming. So the goal here is to simplify the whole process of programming. That means typically these are used for small program development, and I think you'll see why that is as we go to the next slide. But they're also used as a programming teaching tool for teaching people that have little or no programming background, and that was indeed the first usage of them. So these systems have been around for probably the last 15 years or so, and they represent the first application of visual programming usage. And as I said, they're basically replacements for a text-based language. The grain size is something that we're going to talk about quite a bit in the next few slides. Grain size is really what is the atom of a visual language. What's the smallest thing that can be connected to something else to form some syntactically correct statement. And the grain size for a programming language is really the assignment statement or an operator. And that's exactly what it is for visual programming in a programming language also. Frequently, these systems are language-centered, meaning there's been a fair amount of effort to build visual languages around specific computer languages such as Lisp. And that's where a lot of the work has gone on in the past. So some relevant examples here are Prograph, Tinkertoy, VinLisp, which is basically a Lisp-centered language, and High Visual. This is by all means a short list because there's a lot of examples of visual programming languages of this type, and there are some references included with this tape, so you can check that out too. So let's look at one example from a system called Tinkertoy. If we want to do the following operation, which is add two numbers, A and B, multiply that times a third number, C, and then divide the whole thing by D, in this particular language, in Tinkertoy, you would build the structure as following. A and B are integers that are both plugged into this plus operator. The result of that comes out the right-hand side of that plus operator. It is then multiplied by C, which is another integer. The result of that is then sent to the divide operator and divided by D. So as you can see in this slide, on the top of the slide you see the traditional computer language representation of this statement, A plus B times C divided by D. On the bottom you see this visual representation. And clearly compactness is not one of the goals of this system. It's a very visual languages in general consume an incredible amount of screen space, and in this simple example you can see the ramifications of that. So primarily, again, this is used for teaching tools, not necessarily as a full-blown programming language. Some of the problems that occur in systems such as this are that it's very difficult to devise a visual representation for complex operations. How do you really represent a matrix multiply or a matrix inversion with an icon? In this case, the plus star operator and divide operator are very well known by everyone, but it gets much harder as things go, as you get more complicated operators. So let's look at the other side of this, which is the application of visual programming for application creation systems. And here the goals are much different. The goals are, how do you simplify the application building environment? How to build applications easy, or at least easier. And again, the reasons why these tools are more and more in use are because the environments in which we compute are much more complicated. Multiprocessors, massively parallel processors add tremendous complications to the programming paradigm. Graphical workstations can add complications to the programming paradigm if you wish to adequately use them. And then finally, how do you build an application that will run in a distributed environment on several machines, several potentially dissimilar machines that have different floating point representations, etc. So again, the goal here is to empower non-programmers to create applications for themselves. The distinction between this application of visual programming and the previous application is grain size. Here the atom of composition, when you build an application in systems such as these, the atom of composition is usually the function or subroutine level. Now each function or subroutine then is connected together with some graph editor to build a directed graph, which which then is your application. So some good examples of this are primarily from the Unix domain, are APE, which came out of Ohio State University and now is marketed by a company called TerraVisual. AVS, or the Application Visualization System, marketed from AVS Inc. Iris Explorer, which is a system that we're going to use here for demonstration, and Khoros from the University of New Mexico. There's been an awful lot of work lately, at least of late, in the Unix world, although there are some notable examples in the PC and Macintosh world, primarily LabVIEW from National Instruments. So let's look at an example of from Khoros, again from the University of New Mexico. And in this diagram, we see a close-up of the Khoros graph editor, which is called Cantata. So as you'll notice, there are a number of boxes that are connected together. Boxes have glyphs on them. They have ports, which are probably impossible to see in the view that you see on your screen. And these are all connected together with wires to form a data flow diagram. And in this example, we're looking at acquiring an in utero sonogram and looking at the processing of that to isolate the left and right ventricle of a premature baby, which are the two green items that you see in the center of your screen, or the two red small items that you see in the bottom right. So in other words, this is it's a graph-based system. There is a graph editor, a graph creator, in this case called Cantata, that builds this directed graph. You then instruct the system to fire, and in this case modules execute, deriving data in each of the processes and sending data to the last glyph in the chain to produce the data that you've requested. So there is another term which is different, although quite close and conceptually quite related to visual programming, and that's program visualization. In this case, the goal of program visualization is to really understand the execution of an existing program. So a program that's written in a traditional language, such as C or C++ or Fortran, is then instrumented, and the structure of this program is represented visually to aid in the comprehension of the calling order, etc., or where a program is spending an awful lot of its time. So it's really meant to take existing programs and use them to use program visualization to understand it, understand the execution of the program itself. Now, in addition, the reason it's quite related is that in addition to this, most visual programming systems do incorporate program visualization, and you'll see that in the examples that we have in just a little bit. So that's the background on visual programming. Now I want to talk a little bit more about data flow and how it relates to visual programming. So let's get a little bit of background on data flow. Data flow is, again, something that's been around for quite a while. It's nothing new. In fact, there have been computers that have been built around data flow architectures. But in the software systems, essentially data flow is a graph that consists of modules. Modules are, in general, functions with inputs and outputs. The inputs are gathered and are processed by the function to produce outputs. All these modules or functions are connected together into a directed graph, typically a directed acyclic graph, and build an application. So modules typically, as I said before, have inputs and outputs. They also have interactive controls, at least in the systems that we'll talk about today. These controls modify the operation of the algorithm that the module has on its inputs to produce its outputs. Data is transported between modules via connections that are built in a graph editor. In the previous example from Khoros, you saw lines connecting modules, those were created. Basically, that is the data flow itself. So it is essentially in general, a monopartite graph where you have modules which are represented as icons, wires which are the data transport mechanisms. Now, there's a myriad of complications and different ways of doing this, but it sort of all boils down to when do modules execute and how do they transport and how is data transported. So typically modules execute when their inputs are fully satisfied. The question is, who determines when inputs are fully satisfied? And we'll talk quite a bit about that to come. So from this point on in the talk, I'd like to kind of narrow down on a specific class of application creation systems. And it's not really a general presentation of the whole topic, but more one focused on systems such as these. The major components in an application creation system that's data flow based are the following. There is a graph editor, as we've talked about before, and I'll show you how that works in a little bit. There is what I call the life support system, or the execution environment of how modules execute. These typically modules are not, even if they are separate processes, they are not processes that are really self-sustaining, in that they have to be connected to someone else, or connections have to be made for them to really form a full-fledged application. So there is this kind of life support system that is used, which we call the execution environment. It also helps to determine when modules fire and when they don't. There's also a component library. In the visual language, there are these atoms or modules. There may be 50 of them, there may be 100 of them, there may be several thousands of them, and that is what the component library is used to select modules from. So it's essentially a database where you might want to make queries on the component library to say, give me all the modules that accept this type of data on their inputs, or et cetera, or give me all the modules that were made by this institution, et cetera. The last major component is extension tools. That is, how are new modules built? How are they added to the system? Do you need to be the developer of the system, or can end users add new modules to the system? The issues that come into play here are, do you need to program in a traditional programming language to add new modules to the system, or are you even prevented from using a traditional programming language? Can you get access to a programming language, or are you kept in the same visual programming paradigm? In which case, if you are using a traditional programming language, then there is indeed a paradigm shift going from the visual programming environment to this traditional programming language. And then the other aspect of extension tools are, how does one import and export data? These systems tend to be quite isolated, and getting data into the system or getting data out of the system can at times be difficult for non-programmers to do. So let's talk about the graph editor now. Again, this is what is used to create these data flow graphs. The goal of a graph editor is to be able to provide you with components from a component library that you can grab with a mouse, drop down on the graph editor palette, connect modules up to form this graph. So typically modules have a variety of different representations as you go from system to system. From its most simplest representation, a module could be just a name, the name of the function that you want to use, with ports that allow you to connect it to other modules in the system. Or it can have an icon that represents more of a step in a visual language, some iconic representation of the operation that module performs. Or it may even have controls on that icon itself, on that box itself, that allow you to manipulate the algorithm of the module. So modules are wired together to build these directed graphs, and in general, the graph editor is a very interactive support utility, in that you can modify the graph at any time. It's always live. It's always running. So you can add a new module to the system, take a module away, and the graph will automatically recompute, or the environment will automatically recompute the application. So let's go to an example here, which is from Iris Explorer from Silicon Graphics. So what you see on the screen now, on the upper portion of the screen, is a graph editor in the, on the right-hand side. On the left-hand side, a component library where all the components that we wire together reside. So you grab a module from the component library, and you see this, they just have names on them. Drop it down on the palette of the map editor. You can grab another one and drop it down also. In this system, modules, and I'll rotate, just move it around here if we can zoom in on the upper right-hand quadrant. You can see that a module has a name, which is, again, probably not readable here, but it also has widgets attached to it. In this case, there is a text type in, and I'll type in a name for a file. Assuming that I get the right file name. And now the way modules are connected to each other are by clicking on a port button to select the port that you want. This particular module reads an image from disk. We select that, come over here and select an input port from the module that's going to display that, that image to the screen. So here we have the image. It happens to be this image of Africa shot from a satellite. Let's zoom in on it a bit, and you can see the image of what is the simplest data flow diagram possible. One module reading data from disk, executing, firing, sending that data to another module which displays it. So in this example, let's go back and re-execute the module that reads data from disk by selecting a Fire Now menu item. So you notice that the module lights up yellow when it fires. The next module downstream fires after the first module is completed, and we get and the whole graph executes. So let's that's an easy example of, or a very trivial example of what we're talking about. Now let's add another collection of modules that that have been pre-configured to perform some not image processing, but rendering capabilities. And so we can connect from that existing module that reads data off of disk into other modules. And we're going to make two more connections, one more connection. And now that entire chain of modules executes, fires, and displays now what appears to be an image, but indeed is really a three-dimensional entity that we can rotate and zoom in on. So what we're seeing here is the ability of the system to allow you to take to modify the graph at runtime, and essentially everything is live. In fact, it's difficult to make things not live. So in this example, we have the graph executing. One branch of the graph is just displaying an image on disk. The second branch of the graph is taking that image, displacing it in a normal direction based on the luminance of the image, and building this height field. So if we look edge on this image, you can see that there is actually displacement. And in fact, we can modify the amount of displacement by changing a dial on the graph. New modules execute downstream from that dial change, and now you can see a little bit more vertical displacement of that map. Let's talk a little bit about the implications of the graph editor itself. When does this work? When doesn't it work? What are the limitations of in this case, visual programming? So the graph editor is a very useful entity when the number of items that you're going to connect is relatively small, meaning that when you're talking about somewhere around 10 or 15 modules, that's probably the upper limit of really the visual complexity that one wants to really deal with in a visual programming language. From the earlier example that you saw of the language-based example from Tinkertoy, there were 4 atoms that were connected together, and you could imagine that if you had 50 of those, it would be very difficult to understand what's going on. And that is indeed the problem here also. If you have 50 modules connected together in a graph, it resembles spaghetti and is pretty much uninterpretable. So somewhere around 10 to 20 modules is basically the upper limit of visual complexity. If you have atoms or modules that are too primitive, then building a usable graph requires too many of them. If you have atoms or modules that are too specialized, then it's very difficult to interconnect modules together. So this kind of the 7 plus or minus 2 rule really applies here, in that around 7 to 10 modules is a very comfortable feel. So essentially what you're trying to do is always balance this visual complexity with the functionality that you need for an application. This leads to the next point of basically hierarchy. Is the graph editor, does it support the ability to take a collection of modules, abstract them, group them together, abstract them, and build a single visual representation? So let's go back to that example that we're using before. So we'll read in the image that's going to be read from disk. Now read in the next collection of modules that we had previously saved. Connect everything up again. Again, when the module executes, it turns yellow and indicating execution. So here we have a data flow diagram that is relatively simple. There are only 5 modules in it. The question is now, can we take individual modules and group them together? So let's take all the modules except for the last renderer and group them together, building a much simpler diagram. And so now we still have the data flow paradigm, and there are this new group which has been which is right here, shows you that you can collapse all these things all these modules into any groups and build a hierarchical representation of your data flow diagram. This case is a rather trivial example, but we'll talk about some others later on that are much more complex. So what happens when you connect 2 modules together? There are there are 2 different possibilities in graph editors. One is, does the graph editor help you in deciding what is a valid connection, or does it permit any connection whatsoever between 2 modules? So this is basically the strong typing issue. Some graph editors are strongly typed, meaning that they will permit only legal connections between 2 modules. So if not only does the graph editor prevent you from making illegal connections, but in most cases it will direct you visually as to which connections are permissible. In which case, this is all done at connect time. Most systems also have verification at runtime when the data flow diagram is actually, the data flow environment is actually executing, and in which case there is runtime checking of data. And in this case, the data has to be self-describing, so when a module receives it, it knows that this is data of the wrong type. The other possibility is no type checking whatsoever. And this is, of course, much easier to implement a system of this type. It's certainly much more flexible for advanced users in that they can do all kinds of things. You can always find a hack for what you're looking to do, but it is always, it's error prone for all users. So let's talk about data types now for a moment. This determines really when connections are legal. In data flow environments, or in visual programming based data flow environments, there are a couple of different choices. One is you can have a restricted environment, which means you probably have a small number of data types, which the graph editor uses for type checking at connect time. In this case, you can shield end users from all the details of the data type itself. Or you can have a system which is completely open and it has no data types whatsoever, which means that any two modules can be connected together, but they won't necessarily be able to share data. So most systems rely on restricted data types for ease of use issues. And again, just like the grain size of the modules, there's another issue about how many data types are there. If you have a system that has a very small number of data types, then you have maximum interconnectivity. If you can imagine a system that had only one data type, then every module would be able to communicate with every other module. If you have a system that has hundreds of data types, then the chance of being able to connect module A to module B is a very small chance, and so you lose this maximum interconnectivity, but it's a very rich system. So there's always this trade-off between a small number of data types and a large number of data types. The more successful data flow application building systems around typically have a small number of data types, perhaps at most 10. These types are typically very abstracted also. One common data type is an array, a multidimensional array that can be used in its most abstract form. So a module might produce a floating point two-dimensional array on its output port, and the module downstream might accept any type of array, regardless of whether it's floating point or two-dimensional or three-dimensional. So these are more abstracted data types. So now that we have a variety of, we've covered the data type issue, we need to talk about what really is the structure of a module. Is a module a separate process, separate Unix process, or are all the modules bound into a single substrate, which then a controller determines which modules execute? So there's two issues here. I mean, there's two possibilities here. One is the monolithic approach, which is all modules bound into the same process, and it has its advantages and disadvantages. In general, it can be much more efficient, especially on machines where processes are expensive, where context switching is expensive, in that there is no context switching. It's simply basically a function table of modules. Modules become a function table. In this case, it becomes much more difficult to add new modules to the system, in that you have to relink the entire system or rely on dynamic linking to add a new module to the system. And in general, parallelization is somewhat problematic also, in that it's difficult to decide when modules should be firing in parallel. The other possibility is to have a separate process per module. And in this case, the trade-offs are different. Now you have to deal with context switching, switching in one module over the next, and that can be a killer on some machines like PCs, which really don't support multi-processes. The advantages are that parallelism is much easier. In an operating system such as Unix, the scheduling, Unix will basically schedule modules for you. And you no longer have the dynamic linking problem. That is, when you as a user write a new module and add it to the system, it is you simply compile and link that module while the rest of the system is in place. Okay, so now if we go down this path of picking one of these two alternatives of monolithic versus separate processes, we're going to go down. The bulk of the rest of the talk is targeted toward separate processes. So then you need to talk about what is the data and control mechanism of sending information between modules. So there are two types of information that are sent between modules. One is control information, which says you should execute right now. You have your slot at the CPU, so now is the right time to execute. And the other one is, here's data that I want you to execute on. So in general, control is very low volume data. low volume information. It is simply execute with some parameters perhaps. Data potentially could be a very high volume. In the example that we saw before of the image of Africa, that's an image that is probably 300 pixels squared. When we turn that into polygons, it ends up being several, in that case, several 100,000 polygons. And now data becomes, the motion of that data becomes a very relevant issue. In data flow in general, the goal is minimum data motion, meaning that you don't want to make extra copies of data if you can't avoid it, and you don't want to transport data between processes unless you can avoid it, can't avoid it. So the choices are now, do you piggyback the data on the control, or do you use separate paths for data and control messages? If you piggyback data on control, then the bottleneck becomes really this large data transmission if there is a central controller. In that case, the data and the control would need to be transferred back to a central controller and then transferred back to the next process downstream. Or do you use separate paths for data and control information, in which case it's, you have more messaging, but you now can allow for direct module-to-module communication for data passing, and in fact for control passing too. So if we look at the next slide, here's a diagram of one data producer, module A, in the center of the screen, sending data downstream to module B and C. Now these may be separate ports on the output of module A, or they may indeed be the same port. So in essence, we see, in this case, separate independent paths for control, which is going between A and B, and data, which is along the yellow lines. It could be that there is a central controller in a system such as this, and many data flow environments do have central controllers, that the control would go from module A. Module A would fire. It would send control information back to the controller. The controller would then send that back down to module B and say, okay, now it is time for you to execute, and do the same thing with module C. So this brings up the next central question is, when do modules fire? There are two possibilities here. One is a central controller, and the other is a control-free or asynchronous model. In a central controller, the central controller then monitors all data transmissions and all control transmissions from modules. So it is a party to all communication. In this case, it's very easy to prevent extra firings from modules, but in general, it becomes the bottleneck in large graphs. So if you have a graph that consists of 10 modules and you have one central controller, if we're talking about separate processes now, every time a module fires, it sends information back to that central controller and does context switching, maps that controller in, sends a message to it. The controller sends a message broadcasts a message down to all the modules downstream from that first module, telling them that they can execute. So you can get an awful lot of communication. Let's talk a little bit about extra firings. In this very simple diagram of module A communicating its data to module B and C, which both then communicate their data to module D, let's assume that module B is a slow module and module C is a fast module. When A fires, B and C both get information about firing. B is slow, and so it cranks and cranks and cranks. C, if it's computing in parallel, is fast. It finishes its data. It sends it to D. D potentially fires because it has received new data and its inputs may be satisfied enough to fire. When B finally finishes firing, it sends its information down to D, and then D executes again. But clearly in this example, D should only execute once whenever A fires. So in a multi-process application, it can be very difficult to determine, and especially in a control-free application environment, it can be very difficult to eliminate these extra firings. So let's look at what a central controller does. When A executes, it sends its information, its control information, down to a central controller. that controller sends back sends a message now to B and says, okay, now it's your slot at the CPU, you can execute. It sends a message to C. When B and C finish firing, they send a message back to the controller, and then the controller sends a message to D saying that you can fire. So you can see that even in the simple diagram, the central controller could easily be the bottleneck. So what are the alternatives here? The alternative is distributed control. That means giving each module enough information to decide when it should indeed fire itself. This means that the execution algorithm or the firing algorithm is much more complex. Each module needs to know when its inputs are fully satisfied, when it can expect new data on other ports that may be related to ports that have already executed, and then execute itself. This minimizes the bottleneck of the central controller problem. So if we look at this simple example again of A producing data and sending it to B and C, and both of them producing data and sending it to D, when A fires, it sends data and control to both B and C. Both B and C then need to be smart enough to know when they have enough data, and that no other data would be coming in on any other ports. They then fire. They send data down to D. Let's again assume that B is the slow one, and the data from C arrives to D first. This means that now D has two input ports, one from C and one from B. It needs to decide, am I ready to execute now or not? So in some systems, data is tagged along with not only control information, but heritage information. Now the data coming to D would have, on the C port, would have tags saying that this data was produced by firings of A and C. D would then look on its other ports to see, are there any other dependencies on those ports for data from C or A? And it does. It finds that it has one other port which has a dependency on B and A, so it invalidates the data on that port and waits until new data comes in from B, because D has enough information of the upstream topology to know that that new data will be coming in on the B port. And again, this ends up being a large complication for distributed control algorithms, but it more than pays off for itself due to the reducing of the bottleneck, the central controller bottleneck. So let's quickly talk about some details and what are the issues that one needs to be very careful about in building data flow environments such as this, and primarily the execution environment. The first impairment is memory usage. Data must be reference counted, meaning that when in that prior example, when A fires and sends the same data to B and C, A needs to know, or the system needs to know, when it can throw away that data. If A was to fire again, it needs to know that B and C have already consumed that data and that A can replace that data with a new copy. Memory usage in data flow systems is by all means the most difficult thing to work with. There, as you saw in the prior example, there was both fan out from the output of A was fanning out to two consumers, and D had a fan in on one port from two producers. So you have to correctly deal with synchronization on fanning in and out. You have to eliminate the extra firings that we just talked about, and you have to minimize the context switching if there is a central controller, or if the entire data flow environment is all separate processes. And again, to reemphasize, a big problem in data flow environments is how do you minimize data motion? How do you make sure that no superfluous copies have been made, etc. In our prior example, it's possible that A could retain a copy of the data that it sends to B, and B could retain a copy of that. C could also retain a copy of that. So you could potentially have 3 copies of data floating around in that environment, when in fact really only one is necessary, a shared version from all 3 of those. So you really have to minimize data copies and data motion. Finally, other issues such as cycles. Is it possible to connect the output of one module back upstream to one of its ancestors' inputs? And how do you deal with termination sequences and initiation sequences for cycles? And that also gets back to bidirectional data flow, which is the last point. Do two modules communicate with each other in a bidirectional sense, or is data always flowing in one direction? Almost all the examples built so far have single unidirectional data flow. So now let's look at an example, one final example of the system that we're demonstrating today. Here's an initial data flow diagram of a reading data from a tornado simulation. If we look in the bottom, in the lower right, we'll see this data set, which is a contour surface, an isosurface of a tornado. This kind of yellowish structure here is the locus of all points that have the same value within this data set. And on top of it is this blue kind of fuzzy representation, which is buoyancy information throughout it, throughout the simulation. So what does it take to build this diagram, this application, and how do we customize that? So in this example, there are, if we look at the upper right, there are 3 modules on the left-hand side, which all read data from disk. One, the module on the bottom, the lower bottom, generates a color map to map this scalar field of buoyancy into color space. That then goes through a module which creates a volumetric data set of that and sends that off to the renderer. On the top half is another module that reads another set of data from disk, creates the box wireframe that you saw a second ago, and then also that ISO surface, that tan ISO valued surface beneath it, and also sends that to the renderer. So for example, in this example, we want to demonstrate the system to show how you can collapse an entire application, this data flow diagram, into a smaller collection of modules, which can then be viewed in a much simpler context. So let's take 3 modules, the ISO surface, the wireframe, and the renderer, group them together, such as this. Now we have a single group which contains output from those 3. We'll edit that to build a user interface for the system by exposing parameters or widgets that we want to have controls on the system. We'll lay out those controls into a new control panel, essentially a new face for the module, such as this. Here's the rendering window, followed by one control here, which is which controls the ISO surface. We then apply those changes, and now we have a new module which looks like the previous one, has the same interaction paradigms as the previous example, and now allows us to interact with the output simulation in the same manner. So now let's talk about how does this apply to distributed heterogeneous environments. What happens when we want to have modules executing on a whole collection of machines? This means we now have to deal with different data representations, different floating point, different word lengths, different alignment for that matter. We also have different shared resources now. We can no longer use simply shared memory communication for data on different machines because there are no shared memory representations. And now we also have to worry about having brokers on remote machines that deal with transporting data, transporting control, or point-to-point operations. And also we still have to deal with this issue of we have individual user interfaces, graphical user interfaces per module. How are those transported back to the local machine? If we look at this example, Here is now a slightly more complex example from the other diagrams that we've seen. Module A and C are computing on your local workstation. Modules B and D are computing on some other machine, and E and F are on a third remote machine. Now, in Explorer, modules all on the same machine can communicate through shared memory, therefore minimizing data motion on any particular machine. But for example, the data that A communicates with B must be transported across the machine and a data copy results. Also, some machines don't have shared memory. Machines like Cray computers don't have shared memory, so data copies are essential are imperative between two modules on the same machine. So in reality, systems like this typically have local agents and perhaps a central broker that establishes communication between modules and perhaps monitors data transmission. So the blue boxes here there is a separate process, which is a graph editor, which is very important in maintaining interactivity with the entire system, and then a central broker on the local machine, which establishes local agents on remote machines. And those local agents are used for connecting two modules together, killing a module, disconnecting two modules. So let's conclude now by some discussion about does visual programming really work? And it works in certain situations. It works when the graphs are relatively simple, or if hierarchy is fully supported. It also works when the data typing is really effective, meaning that typically this works best for domain-specific, discipline-specific applications. This occurs in the computational sciences, scientific visualization, image processing. Some database systems have been built on visual programming. When doesn't it work very well? Well, it doesn't work very well for very high-performance systems. You'll never really be able to build a system that will perform as high as a specialized application by using data flow and visual programming. It also does not work well for fixed functionality applications. Again, visual programming is best used for applications where the configuration of the application is not known by the original developer but is determined by the end user. And finally, as a conclusion, what are the limitations of visual programming? Well, typically, it's difficult to scale a visual programming graph to large applications. And here, hierarchy is essential for any of this to work. Once you have a large number of modules or atoms that you're compositing together, say in the thousands, the component interface really becomes a limitation. How do you find the module that you're really looking for? You need a good component library paradigm. You also, as I said before, the efficient memory utilization is very important for data flow. Is there one copy of data per module per port? Is data shared between modules? These become crucial issues in data flow environments. And finally, the issue is there's always a difference between prototyping versus production. While data flow and visual programming is typically very good for this exploration process, this exploratory, how do I combine these things together to meet this one particular need, it sometimes is difficult to transition from this exploration process and the needs of that to the very flexible needs of that to very specific needs of production of now that I've got the image that I want, how do I get 1,000 more of them and fast? So those are the primary issues that one needs to deal with in terms of limitations for visual programming and data flow environments. Thank you.